Hello, Chem 212 students, and welcome back for another week of lectures. This week we're going to be doing Chapter 3, which is all about acids and bases. We're going to be heavily using what we've learned previously about resonance in Chapter 2. And so that will be very important. We'll also be using curved arrows to, for the first time, show chemical reactions and not just resonance. And so let's begin. Here's just kind of a little primer in terms of organic acids and bases. You'll find them all over the place. Your stomach acid is quite acidic with a very low pH of 1. So low pHs below 7 indicate acidic solution, and higher pHs for a solution will indicate a basic solution. And so we have, pure water here being neutral, milk slightly acidic, and so forth. Some fruits and being acidic here. In addition, we've got eggs and baking soda and soap cleaners, as you can see on the high end, being mostly basic right here. Okay. And here on the side you have a picture of an acid-base titration, which you've probably done quite a few times already. All right. So in terms of the definition of the acids and bases, we're going to be focusing mostly on the Bronsted-Lowry definition. The Bronsted-Lowry definition is written such that acids are those that donate a proton. Generally, a proton is the H+1 ion, H+, and so those substances that can have an H+ be released from them, or H+ gets removed, those are the acids. And the bases accept a proton, so that could be one of many molecules or ions that accept a proton. The classic example is hydroxide, which has a negative charge. The negative formal charge is actually on the oxygen here, but that's not the only thing that can accept a proton. Other things can as well. For example, water. Water has a property that is called amphoteric, meaning it can behave as either an acid or a base. In fact, it does so with itself. One water molecule can donate a proton to another. We call that the autoionization of water. Now here we see in this classic example we have the strong acid HCl, hydrochloric acid. Why is HCl a strong acid? You've probably wondered that in the past, and today we're going to discuss the exact reasons why some acids are stronger than others and some are weaker. You've probably got a little bit of that in Chem 151, but we're going to go into greater detail today. So the H here is what can be released as an H+, and something you want to notice here is that the electrons are going to be left behind on the chlorine. And so the way we're going to be writing that later is we're going to say, okay, these two electrons in this bond, these are going to be left to the chlorine. And the water here is going to now be creating a bond with the hydrogen. That bond, this arrow should be going to the hydrogen. I'm trying to point it there. This lone pair will now create a bond with this hydrogen, which has taken none of these electrons with it. So you can see that all 8 electrons are left on the chlorine, giving it a negative charge, a negative formal charge as well. 8 dots compared to the 7 valence electrons that chlorine would normally have. And then the oxygen here has a positive formal charge because it's making 3 bonds and it has 1 lone pair. So hopefully you're getting used to those patterns for oxygen and nitrogen and carbon. When you see how many bonds and lone pairs they have, you can very quickly determine the formal charge now after some practice in Chapter 2. Now also we should consider these definitions of conjugate acid and conjugate base. So a conjugate acid is the substance that results when a base has accepted a proton, and a conjugate base is the substance that results after an acid has given up a proton. So for example, in the reaction we just looked at, HCl was the acid, water was the base, and then the HCl lost the proton, so it loses H and it loses plus. So the charge goes down by 1 unit, as we saw when we looked very closely in the last slide at the electrons. Charge goes down by 1 from 0 for HCl to -1 for the chlorine, because the hydrogen left the electrons behind in the bond when it left. The base here has accepted a proton, and it makes its conjugate acid H3O+. So you can see the conjugate acid is what you get out of the base once it grabs a proton. And so we can see it has 3 H's now, but also it has a plus charge, because remember, it's not a hydrogen atom that it's accepting, it's an H+1 ion. And so it is lacking in electrons, and so you can see that the charge goes up by 1 unit. So when you gain an H+, the charge goes up by 1 unit. And we go here from 0 to +1. When you lose an H+, the charge goes down by 1 unit here from 0 down to -1. So that's a little shortcut you can keep in your mind. And so now if we want to look at this, we should label the acid, the base, and the conjugates. Well, here in this case, we can see that this H is written in red here. And we're going to see that in fact the reaction will proceed quite nicely to the right, in the rightward direction. In terms of this equilibrium, it will be more favored to the right side and and significantly less favored to the left. So this H+ is going to give up or this water is going to give up an H+. And so this H+ will now attach itself to the oxygen. When we begin using arrows, we'll say that this lone pair is used to create a bond to the hydrogen, and then this hydrogen, when it leaves both electrons behind. And so that bond here is now going to be left as a lone pair on the oxygen. And so you can see in this case, it was the water that gave up its protons. So it is the acid in this reaction, written on the left. And the oxide ion here, it's not an oxide, it's a oxo ion. It is the base, because it's accepting the proton. The H+ is attaching now to this oxygen. And so now once the H+ is attached over here, we would call this the conjugate acid. The conjugate acid of the original base. The conjugate acid of the original base. And now the water has lost a proton, so what you have left behind is the hydroxide. So this would be called the conjugate base of the acid. And notice the difference. The difference is always 1 H+ ion, 1 proton. So when you have a conjugate acid, it has 1 more H+, and you can see it has an H attached now, and the formal charge here is gone, because now this lone pair has been used to make a bond, and the oxygen has 2 lone pairs and 2 bonds. For the acid, which in this case is the water, so you can see here in the previous reaction it acted like a base. In this reaction it reacts like an acid, because water is amphoteric. It can do either one. And this H+ leaves, and these 2 electrons are left behind. So the result is this oxygen has 3 lone pairs and is making 1 bond. It has a -1 formal charge here. So let's do this a little bit more. Let's draw reasonable products for these reactions here. And again, we're going to have a reaction where water is acting like an acid, and another one where it's acting like a base. So this is telling us, okay, let's make the water behave like an acid. So it's going to give up its H+. And so what that means here is that the nitrogen is going to go and make a bond with the hydrogen. So this lone pair is what's going to be used to make the bond, and those 2 electrons will make a coordinate covalent bond here with the hydrogen. And remember, the H+, when it leaves, it does not take any electrons with it. It's just a proton, no electrons. And so these 2 electrons in this bond are left behind on the oxygen. And so in the end, we end up with a nitrogen that is making 4 bonds. And so it has another hydrogen here. This is the one that just got there. and it has a bond to a carbon here and a bond to a carbon here. And so since this is nitrogen is making 4 bonds and has no lone pairs, it has a +1 formal charge. Now the oxygen here, it it is now got 3 lone pairs because that bond, the electrons in this bond here were left behind on the oxygen. And it has 1 bond, so it has a -1 formal charge. Okay, and now this base with the nitrogen atom, and you're going to see that things with nitrogen atoms tend to be bases, organic bases. When you see a nitrogen atom, your alarm bell should be ringing on a neutral compound at least, that, oh, this can behave like a base, for reasons that we'll continue to discuss here. So this base has now gained an H+. This is the one right here that was added. Right there, that one. And so now we're going to say, whoops, that we're going to label this guy here. This is the conjugate acid, because it's what you get from this base when you add an H+ on. And now for the water, it has now lost an H+, so you get hydroxide ion, which is the conjugate base of water. It's what you have when the water loses an H+. And so you can see that the charge goes down by 1 and H is gone there. Now for the products of the next reaction, we've got now this compound is going to behave like an acid. In reality, it very rarely behaves like an acid, as we'll see. However, if it were to behave as an acid in some situation, it would lose its H+. And so the water is going to get the H+. And so what's going to happen here is this lone pair now is going to be making a bond to this H. Both of these electrons are going to be used to make the bond. These 2 electrons in this bond are going to be left behind on the nitrogen. Okay, and so now we can draw the product structures. And so this nitrogen will now have two lone pairs. So the one right on the left here and the new one added from the electrons left behind when this hydrogen leaves, and it will have 2 carbon atoms bonded to it. And so this is a nitrogen with 2 lone pairs and 2 bonds, so it has a -1 formal charge. And this would be the conjugate base of the acid. And now the this oxygen here is now making 3 bonds to hydrogen. And it has 1 lone pair remaining. The other lone pair was used to make the bond to the hydrogen. And so this oxygen has a positive formal charge, and this is a hydronium ion. And this would be the conjugate acid of water. It's what you get when water has an H+ added to it, conjugate acid. And so you can see here, an H+ has attached. It brought no electrons with it, which is the reason why the charge goes up by 1. When that H+ leaves, it leaves the electrons behind, so the charge goes down by 1. That 1 extra electron that it previously had in its region, but no longer does. It's all in the nitrogen base. Okay. So what you've been seeing me do with these electrons is I've been using these curved double arrows. And the way in which we use these is different than when we use it in resonance. For example, one of the cardinal rules of resonance was that you never started an arrow from a single bond, because that would break the bond, and that would be a chemical reaction. When bonds break or are made, that is a chemical reaction. That's not resonance. Resonance is when the electrons are delocalized and they can move around the structure of the molecule, and we represent the way that they can move by these double-headed arrows. But here, the way we use the double-headed arrows is different. We are now using it to create bonds. So this double-headed arrow from this base is being used to show the creation of a bond to this hydrogen atom. And the double arrow here, away from this single bond to the anion here on this acid, is breaking a bond. So bonds are being made, bonds are being broken. That is different than resonance. That is a chemical reaction. And what we're showing here with these arrows is the beginnings of what we're going to call mechanisms. And mechanisms are going to be step-by-step descriptions of organic chemical reactions that show exactly the order in which and the way in which bonds are broken and bonds are formed in a chemical reaction. So in the past, in general chemistry, we were mostly interested in what are the reactants and what are the products. When you studied kinetics, we briefly, or in your class, you briefly would have heard about this idea of mechanisms, where a reaction that we observe, that we see very obviously some reactants and some products, actually itself is composed of many individual reactions that when they happen in sequence, they produce the overall reaction that we observe. Often these reactions happen so quickly that we don't notice that they're even happening. We're going to be going into more detail on mechanisms. We're not only going to state the reactions that are occurring, but exactly the order in which bonds are being formed and bonds are being broken. And mechanisms are going to be one of the primary focuses of this class as we move towards the middle and the end of the class. And in Chem 213, you'll have mechanisms all the time. Mechanisms are very valuable because if you understand why each step is happening, then you don't have to memorize exactly all the beginning, like the reagents and the products of the reaction straight up. You don't have to memorize them. You can understand the steps by which a reaction will occur and why they will happen, so you won't have to memorize products or the way in which a reaction will go. You'll understand it instead, and that's why understanding mechanisms will be key. So this is just the beginning when it comes to our discussion of mechanisms and using double-headed arrows to describe the steps in a reaction. So here's another reaction with an acid and a base. So the acid here is this carboxylic acid, so you should note the functional group. Here we have a carbon double bonded to an oxygen. It also has an oxygen with a hydrogen attached. That is a carboxylic acid, and it does behave as an acid for reasons we'll discuss very soon. And then we have the hydroxide base here. And so the acid is donating its proton, which is being bonded. We're using this lone pair from the hydroxide. These electrons are being left on the oxygen atom to create this oxoanion here. We're going to use a certain terminology when we describe mechanisms like this. We're going to use the word attack when a lone pair is going and making a bond somewhere with an atom. We say that it attacks it, to grab it basically and make a bond with it. The acid won't just lose its proton. There's got to be a base. Even if that base is hydroxide or water, something will take it off the acid. There needs to be a kind of a pull a little bit to help it come off. And this shows two arrows. So these two events here are occurring simultaneously. So let's do another curved arrow exercise for the acid-base reactions. And I think I did actually this same one earlier when I showed you the example. But this is the base, so it's going to be accepting the H+, so it's going to go over here and grab it, and then this will be left behind. And as we saw in the example before, this nitrogen now has 2 bonds to hydrogen. It has 4 bonds and no lone pairs. It has a positive formal charge. And the oxygen now has 3 lone pairs because this bond was left behind here as a lone pair. And the hydrogen atom here, this has an oxygen with 3 lone pairs and 1 bond. It has a negative formal charge. Here's another example. And so here, when you're looking at a mechanism, you should also be able to recognize what is grabbing the proton, what is releasing it. Also, something you're going to notice that's a little bit different about this is that one of the reactants has been placed above the double-headed arrow in this equilibrium. And that's something you're going to see more and more commonly in the writing of organic reactions. We often write a key reagent instead of saying the base here plus the acid. Sometimes we'll write a key reagent above the arrow, meaning that we add this, and then the next step we add this, and so forth. And so this is a little bit different way of writing chemical reactions that you're going to see more and more in your textbook. And so here we can see that this oxygen is grabbing the proton, so it is behaving as the base here. So this is the base, and it is the hydronium ion that is giving up the proton, so it is the acid. And notice the acid component has been written above the arrow. Again, this is going to be something we see more and more later. And now we have a single arrow, meaning the breaking of a bond here. And so this bond is being broken right here, and water is leaving. And that's going to be something we'll see later on too. And so you can see above the arrow what was written was minus H2O, meaning this water went away somewhere. It's gone, and so we just now wrote what was left over, and that was the carbocation, because this carbon was making 4 bonds and had no lone pairs, but now it's making 3 bonds and has no lone pairs, so it has a positive formal charge. And at that point, a double bond could be formed here if the water will remove the H. So the problem is we can't make a double bond right now, because if we look at this very closely, when it started, it had 3 hydrogens. And so you can't make a double bond to this carbon, because then it would have 5 bonds and it would exceed an octet. But what can happen is that a water can come by and take the extra H atom, and then at that point you'll only have the other 2 hydrogen atoms left. Well, I'll actually write it over. Yeah, I'll write them here, but these are going to be the ones that are left, that are right here. So now this carbon's making 4 bonds. And so in this case, it was the water that was accepting the H+, and so it's the water now behaving as the base, and this compound here is giving up its H+, and so this would be the acid. And so that's an example of the kinds of mechanisms we'll be seeing as we move forward in the class. And a lot of these mechanisms involve acid-base type reactions. And so that's why we're covering this acid-base stuff now early, because we can't really talk about a lot of mechanisms without talking about the acidic and basic parts of those reactions. So you may remember from general chemistry that there were so-called strong acids and weak acids, and strong bases and weak bases. Just very quickly, now you probably have memorized these. These are very useful to memorize. But strong acids included HCl, HBr, and HI. They also included nitric acid, HNO3, perchloric acid, HClO4, and sulfuric acid, H2SO4. So a good question is, why are these acids so strong? Why do they so easily give up their H+ to water? And that's a question we're going to answer in great detail today. In terms of strong bases, it's a little less interesting. The strong bases are generally just those that dissolve in water to make hydroxide ions. So lithium hydroxide, sodium hydroxide, potassium hydroxide, and in fact all the group 1 hydroxides. And then calcium and beryllium and magnesium hydroxide are not considered strong bases, only because they're not very soluble in water. But if you remember your solubility rules, but calcium hydroxide, strontium hydroxide, barium hydroxide are all considered strong bases. And what they have in common is they put hydroxide in water. And hydroxide is quite a strong base for reasons that we will discuss. So we're going to discuss the strength of the acids both quantitatively And so remember, we've talked about quantitative and qualitative, right? Descriptions of things. Previously, we discussed these in terms of error. How would you quantitatively describe the error in your experiment using numbers? How would you qualitatively describe the error in your experiment using words? We're also going to have quantitative analyses of the strength of acids, comparing their Kas, or more specifically in organic, we like to compare their pKas. And you may recall that like pH is the minus log of the H plus concentration, for example, right? And likewise, a pKa is going to be the minus log of the Ka. We'll also do qualitative analysis by comparing the structures, so that even if we don't have the pKas available, we should be able to determine the relative strengths of acids anyway. Okay, so a quantitative analysis of strength, we would need to actually make a measurement. Remember Ka from general chemistry? So in terms of Ka, what does it look like? Well, if you have an acid, here we have a generic acid, HA. So H is the H plus that we'll remove, A is the rest of the substance there, and water. And so the H plus, this isn't a mechanism, this is just kind of describing the H plus going from the acid here to the water. And so it loses the H plus, and so the H is no longer attached to the rest of the molecule here, and the charge goes down by 1 because you lost H plus. For the water, it gained an H, but not just an H, it gained an H plus, so the charge goes up by 1 unit from 0 up to positive 1. And to write a Ka, we write products over reactants, and so it's going to be the product ions here, A minus and H3O plus, over the reactant. Remember, water's not included, it's the bulk material. We only include aqueous substances and ions, and so all of these would be considered aqueous except for water, which we call liquid. It is the bulk liquid. All of this is happening in water. So note the form of the K here. The more acidic the substance is, the more this reaction will go to the right. And so that will mean that at equilibrium, there will be more of this H3O plus and A minus and less of the HA. So a high Ka means more acidic. The higher the Ka, the more acidic the acid is. But what we're going to be looking at is pKas. And what we're going to see is that the lower the pKa, the more acidic. And the reason why this is true is because, as we're going to see, the pKa equals the minus log of the Ka. So the bigger the Ka is, the larger this number will be, and so it will be a larger negative number. Kas can only be greater than 0, and generally, a lot of times they're negative, they're not negative, they're less than 1, which would result in a negative log. But basically, the bigger the Ka, the smaller the pKa will be, because of this mathematics. And so a larger Ka is more acidic, but we're going to be looking more at pKas. So a smaller pKa will indicate a more acidic acid. So in terms of, as I said, Ka values, they're always greater than 0. Sometimes they're less than 1, though, so they can go from like around 10 to the minus 50 to 10 to the 10th power. This is a huge range of numbers, which is why we use pKa. It's just much more convenient in terms of numbers. These numbers are, very big and very small. They're not very convenient. So we take the negative log of the Ka, and we get the pKa. Okay, and so if you take these values, remember log is the opposite of 10 to the power. And so if you take the log of 10 to the minus 50, you get minus 50. It basically eliminates the 10 to the power. And then the negative of minus 50 is 50. So that's where you get this high end to the Ka. So you can see if the pKa rather, you can see if the Ka is very small, this is a very small Ka, that leads to a larger pKa. So they're opposite in terms of their size. And 10 to the 10th power, so likewise, if we take the log of 10 to the 10th power, the result is 10. And so that would be the log of the Ka, then we put a minus, so that would be minus 10. So that's this lower end here. So as you can see, the bigger the Ka, the smaller the pKa. Like here, bigger Ka, smaller pKa, it can even be negative. And the smaller the Ka, the bigger the pKa. And remember, a higher Ka means more acidic. More acidic. More acidic. And this, it would be less acidic. So strong acids will have low pKa values. And so here are some pKa values. Not all of them, obviously there's lots more, but these are some nice examples. So here you have, this is sulfuric acid. This is H2SO4. And you can see that its pKa is tiny. That's because it's a very, very strong acid. It's one of our 6 strongest acids. Now there are stronger acids, but it's the 6 that are common. And anything any stronger, you have to, it's kind of irrelevant in water, because as we're going to talk about, any acid dissolved in water can only be as strong as hydronium, because it will be converted into hydronium. It's stronger acid than hydronium. And hydronium, again, in case you forgot, is H3O+. That's hydronium, which is the strongest acid possible in water, because any stronger acid reacts to form hydronium instead. So remember that in logs, a difference of 1 is indicating a power of 10, right? That's why we use logs. So if we have, for example, if we compare the pKa of sulfuric acid to hydrochloric acid, we can see that the difference is 2, which means that the sulfuric acid is 10 to the second power, or 100 times stronger than HCl. But they're both considered strong acids, right? Why is that? Because they're both stronger acids than hydronium. So here's hydronium. Hydronium is the strongest acid you can have in water. Any acid that is stronger will react with water to create hydronium. And this is going to be called leveling, and we'll talk about that near the end of the chapter. So these are strong acids, stronger than hydronium. And this is not a type of strong acid we've covered before, because it's not neutral. When you discuss acids before, you only consider neutral acids, not these that are ions. Then we have carboxylic acids. So again, you can see there's a carboxylic acid because carbon double bond to oxygen, which is bonded to oxygen, bonded to hydrogen. And then a little less strong than that are this structure right here, where we have a hydrogen atom on a carbon in between 2 of these carbon double bond to oxygen, slightly less acidic. We've got a phenol, slightly less acidic than that, and water, which is significantly less acidic. And then alcohols, less and less acidic. Here, okay, and until you get alkanes, which are very, very not acidic at all. So you can also use the pKa values to compare the strength of bases, of the conjugate bases. So the stronger the acid, what that means is it's willing to give up its H+. It really will very easily give it away, which means that the base here is a very weak base. If an acid is strong, that means it's going to give up its H+. And the resulting conjugate base is going to be very weak because it's not going to grab H pluses back. Because as soon as it did, it would make this, which would want to give up its H plus again. And so the stronger the acid, the weaker the conjugate base will be. So when we want to compare the strength of bases, what we can do is add an H plus and see which acid they are. The weaker the acid is, the stronger the base. And that's going to be our strategy for determining the relative strength of bases, is we will figure out what their conjugate acid is and then use various qualitative types of rules of thumb to help us decide which is the stronger or the weaker base, the stronger or the weaker acid in the case we're given an acid. So a base with a very large value of Kb, will its conjugate acid have a low or high pKa? Okay, this is a very interesting question and well stated, I think, because it asks you about Kbs and Kas and pKas as well. So you have to keep all of this straight. So let's write down what we know. A larger Ka is going to be a smaller pKa, which is going to be both mean more acidic. And a same thing is for Kbs, except for with bases. So a larger Kb is going to be a smaller pKb, which is going to be more basic. Also, we know the stronger the acid, the stronger the conjugate acid, the weaker the base. And so if a base has a very large Kb, then the conjugate acid would have a very low Ka. Okay? And a low Ka indicates a high pKa because they go opposite. So the conjugate acid will be a terrible acid if the base is great. They go opposite to one another. So with the conjugates. So if we have a base that is a very strong base because it has a large Kb, that means the conjugate acid will be very weak, meaning so this will be weak conjugate acid, which means a low Ka, which indicates a high pKa. So for example, if we had a very strong base, for example, the chloride ion, a very weak base. This is a very weak base. Let's go to a very strong base. We have a very strong base, like this ion here. Its conjugate acid will be very weak, so its pKa will be quite large. So that's how you answer that. So how will we use pKa's to analyze this equilibria now? How we can now, given the relative pKa's of an acid and the conjugate acid of a base in a reaction, we can decide which direction the reaction will go. And in general, the rule we're going to use is that if the reaction is going to go from the stronger acid and base to the weaker acid and base. So here is a stronger acid. This here is the stronger acid. I can tell because then this conjugate acid here, this is the weaker acid. And I can tell that because the pKa is smaller for water than it is for this conjugate acid, the tert-butanol. So the reaction here is going to go quite strongly to the right and more to the left. We can even, based on the relative pKa's, approximate how much more of the products there will be than the reactants, because the difference here is 2.3, so I'll just approximate that as 2. So the pKa difference, so 18 minus 15.7 is 2.3. So I'm going to call this approximately 2. And and then 10 to the second power is 100. So remember that these are logs, and so they are, each value of 1, each difference of 1 represents a difference of 10 to the first power. So since the difference is 2, this is 10 to the second power in difference. So we would expect at equilibrium for there to be approximately 100 times, even a little bit more, 100 times more of the products than the reactants. And so we can compare the relative strengths of the acids and the bases to determine which direction the reaction will go. The reaction will go from the stronger acid and base to the weaker acid and base. Stronger acid and base to weaker acid and base, which in this case is to the right. The right will be strongly favored here at equilibrium. Much more of these products than reactants equilibrium. So here's another example where we have relative pKa's here, and we have a mechanism drawn. So there's a base here. It's a carbanion. Carbanions are extremely strong bases because their acids are extremely weak. This is just not acidic at all, the conjugate acid. And so, but the base here is quite strong, and so, but not as strong as this one, right? So we can see that here. So we compare the Ka's. This is the stronger acid on the left, the stronger acid, compared to the conjugate acid that is formed from the base when it grabs an H+. This is the weaker acid. So this reaction is going to go extremely strongly to the right because this difference is so big. So we always go from the stronger acid and base to the weaker acid and base, because the stronger acid wants to give up its proton. It's going to really, and the base really wants it. And so that's always going to be the case, that the equilibrium favors this. And the difference here is about 34. So this is going to be about 10 to the 34th power more of the products here than the reactants. So this can't even really be considered an equilibrium. So you can see in these cases we might write a one-way arrow, just indicating that this is just going all the way to the right. It's hardly going to the left at all. Very, very little. So here's another practice problem. Provide the products and the curved arrows for the following acid-base reaction. And so we would need to figure out which is going to be the acid and the base first. And so we'll have ways of doing this. But what we're going to see is that this is going to be more acidic. And I'm going to do this just in a quantitative way by comparing the pKa's. So let's look back and see. We'll see that this here on the left is a very strong acid. If we look at the patterns in this pKa chart, it is quite a lot like this situation here, or hydronium. It has a oxygen with a hydrogen attached and a positive formal charge. Very acidic. And so it's going to behave as the acid, and the alcohol here will behave as the base. And so we'll draw some arrows. So since this is the base, it's going to grab the H+, it's going to attack it, we say, and make a bond with it. And then it's going to leave as an H+, so it's going to leave both of these electrons behind. And so now we can write the resulting structure of the 3 bonds to carbon here. We have this oxygen, which now has 2 lone pairs and 2 bonds, and so it's much more stable. That's part of the reason why it's so acidic. It's because the conjugate base is stable, and the acid itself is not, with that positive formal charge on the oxygen. We learned in chapter 2 that positive formal charges on oxygen are not very favorable, right? A negative formal charge is more favorable than a positive one would be. And now we have this oxygen, which it will now be making itself 3 bonds, and we'll have 1 lone pair, so it will have a positive formal charge here. And so that will be that acid and base reaction. So I'm just labeling these. This is the acid, this is its conjugate base, and here this is the base, and this is its conjugate acid. So now that we've discussed the basics of how to compare acids in a quantitative way using pKa's and how that relates to the equilibria, we're going to next talk about how we can compare the relative acidity of acids even if we don't have the pKa's that were determined experimentally. We can actually compare the acidity by simply using or simply looking at the structures and using our knowledge of the relative stability of ions and resonance structures to determine which will be the stronger acid and which will be the weaker acid. And that's what we're going to do in the next video. I'll see you there.